morning. Today we discuss about the Pn junction. What is a Pn junction? What is the thermal equilibrium condition? What is the band diagram, etc. So first of all, we discuss what is the thermal equilibrium condition for a Pn junction. The most important characteristic of a Pn junction is that they rectify, that is, they allow current to flow easily only in one direction. We now show a figure which shows the current voltage characteristics of a typical silicon Pn junction. When we apply a forward bias to the junction, that is positive voltage to the P side, the current increases rapidly as the voltage increases. However, when we apply a reverse bias, virtually no current flows initially. As the reverse bias is increased, the current remains very small until a critical voltage is reached, at which point the current suddenly increases. This sudden increase in current is referred to as the junction breakdown. The applied forward voltage is usually less than 1 volt, but the reverse critical voltage or breakdown voltage can vary from a few volts to 1000 volts depending upon the doping concentration and other device parameters. We now discuss the band diagram. In the figure which we have shown over here, we see two regions of P and N type semiconductors that are uniformly doped and physically separated before the junction is formed. We note that the Fermi level EF is near the valence band edge in the P type material and near the conduction band edge in the N type material. While P type material contains a large concentration of holes with a few electrons, the opposite is true for N type material. When the P and N type semiconductors are joined together, the large current carrier concentration gradients at the junction cause carrier diffusion. Holes from the P side diffuse into the N side and electrons from the N side diffuse into the P side. As the holes continue to leave the P side, some of the negative acceptor ions, that is Na-, near the junction are left uncompensated since the acceptors are fixed in the semiconductor lattice, whereas the holes are mobile. Similarly, some of the positive donors, Nd+, near the bottom, near the junction are uncompensated as the electrons leave the N side. Consequently, a negative space charge forms near the P side of the junction and a positive space charge forms near the N side. This space charge region creates an electric field that is created from positive charge towards negative charge, as we have shown in the diagram. The electric field is in the direction opposite to the diffusion current for each type of carrier charge. The lower illustration in the figure shows that the whole diffusion current flows from left to right, whereas the whole drift current due to the electric field flows from right to left. The electron diffusion current also flows from left to right, whereas the electron drift current flows in the opposite direction. We note that because of the negative charge, the electrons diffuse from right to left opposite the direction of the electron current. Now we discuss what are the equilibrium Fermi levels. At thermal equilibrium, that is in the steady state condition, at a given temperature without any external excitations, the individual electrons and hole current flowing across the junctions are identically zero. For each type of carrier, the drift current due to the electric field must exactly cancel the diffusion current due to the concentration gradient. So we have this equation: Jp is equal to Jp drift plus Jp diffusion, as we have shown over here. That is equal to Q mu P Pe minus Q dP dP by dx. This is equal to Q mu P P in brackets 1 by Q dE1 by dx minus Kt mu P dP by dx, that should be equal to 0. Where we have used equation for electric field and Einstein relation, dP is equal to Kt by Q mu P, and if we substitute the expression for hole concentration, P is equal to Ni e to the power in brackets Ei minus Ef bracket close divided by Kt, and its derivative dP by dx is equal to P by Kt in brackets dEi by dx minus dEf by dx. This is what we have obtained for the equilibrium Fermi level. So the equation yields the net hole current density as equal to Jp is equal to mu p dEf by dx, this is equal to 0. dEf by dx, this will again come out to be 0 because the constants are there. So we obtain the net electron current density Jn is equal to Jn drift plus Jn diffusion. This is equal to q mu n E plus q dn by dx. So this is equal to mu n dEf by dx, this should be equal to 0. Thus the condition for 0 net electron and hole currents, the Fermi level must be constant, that is independent of x throughout the sample, as is shown in the energy band diagram. The constant Fermi level required at thermal equilibrium results in a unique space charge distribution at the junction. We repeat the one-dimensional Pn junction and the corresponding equilibrium energy band diagrams. The unique space charge distribution and the electrostatic potential are given by the Poisson's equation as we have shown over here. That is d square psi by dx square is equal to minus dE by dx, this is equal to minus rho s by epsilon s, this is equal to minus q by epsilon s in brackets nd minus na plus p minus n bracket close. So this is the Poisson's equation. Here we have assumed that all donors and acceptors are ionized. In the regions far away from the metallurgical junction, charge neutrality is maintained and the total space charge density is 0. So for the neutral regions, we can simplify this equation to d square psi by dx square is equal to 0 and nd minus na plus p minus n, this is equal to 0. For a p-type neutral region, we assume nd is equal to 0, p is very much greater than n. The electrostatic potential of a p-type neutral region and with respect to the Fermi level is designated as psi p. We can obtain by setting nd is equal to n is equal to 0 and by substituting the result p is equal to na. So psi p is equal to minus 1 by q ei minus ef. This is for x less than equal to minus xp. So this should be equal to kT by q ln na by na. Similarly, we obtain the electrostatic potential in n-type neutral region with respect to the Fermi level. So we get the Pn junction and the Pn junction diagram is shown over here. Here we have a for the Pn junction, the electrostatic potential is plotted in the y-axis and we have the dimensions of the crystals in the x-axis. So when we join the bands at the junction, we get a figure of this type. This figure shows this is for an abrupt Pn junction. So this is a Pn junction with abrupt doping changes at the metallurgical junction. The energy band diagram of an abrupt junction at thermal equilibrium. This is the equation. This is the band diagram for a Pn junction at thermal equilibrium. Then we have the space charge region. This is for abrupt Pn junction. The diagram can be seen. We have very much abrupt boundaries over here. There is a neutral region, there is a transition region, there is a charge density due to uncompensated impurity ions, there is a depletion region, neutral region, transition region. This is what we obtain. And then we have the rectangular approximation to the space charge distribution as we have shown earlier. So this we have shown the Pn junction and then the equation psi n is equal to minus 1 by q ei minus ef in brackets for x greater than equal to xn, this is equal to minus kT by q ln nd by na. The total electrostatic potential difference between the p side and n side regions, neutral regions at the thermal equilibrium is called the built-in potential. So the built-in potential VBI, this will be given by psi n minus psi p is equal to kT by q ln na nd by ni square. Now we have this for the space charge region. For the space charge region, what happens is that Moving from neutral region towards the junction, we encounter a narrow transition region. The space charge of impurity ions is partially compensated by the mobile carriers. Beyond the transition region, we enter a completely depleted region where the mobile carrier densities are 0. These are called the depletion region, also called the space charge region. For typical PN junctions in silicon and gallium arsenide, the width of each transition region is small compared with the width of the depletion region. Therefore, we can neglect the transition region and represent the depletion region by the rectangular distribution as we have shown earlier, where xp and xn denote the depletion layer widths of the p and n sides for the completely depleted region. With p equal to n equal to 0, the equation finally becomes d square psi by dx square is equal to q by epsilon s Na minus Nd. The magnitudes of psi p and psi n are calculated and are plotted as a function of doping concentration of silicon and gallium arsenide. For a given doping concentration, the electrostatic potential of gallium arsenide is higher because of the smaller intrinsic concentration. Thank you.